Hi everyone. I have been an engineer for several years. This year I'm at Canterbury University trying to do a master's degree along with AdScale laboratories, and I'm just going to give you a little bit of a tour of some of the data science work that I've been doing. I'm going to try and give a live demo while we're at it. So that script there is busy launching a Hadoop cluster. So I'll leave that. We'll get to what's going on there in just a second. So this may help you in situations where you've got more data than you can comfortably deal with using the fantastic tools that we've seen so far, like IPython and pandas. First, I'll talk about the context of the industrial problem. Then I'll talk about processing data larger than memory with Python. Then I'll talk about prototyping things, algorithms. And finally, I'll make a couple of comments on array manipulation and porting these things to production. So the first question to ask when embarking on any data science project is, how is it going to generate revenue? A lot of people say, look, we've got all this data, let's just analyze it and see what happens. It doesn't really work like that. You need to have a clear path to people giving you more money for what you're doing. Oh, shit. Sorry. A bit nervous here. So another question is, what's not being measured? A lot of big data systems run off automatically generated collection systems. So an important question to ask is, what's not being measured? What's the collection system missing? Because when you analyze the data, you won't see that. A great example is this is some PhD research at Harvard studying depression on a Google queries. If I'm depressed and it's just me and I'm Googling depression, or if I'm depressed and I have 50 friends and they're all Googling depression to try and help me, that's one search versus 50 searches for the same person. Aggregate statistics in this case are unlikely to be helpful. Now, the context of this problem is computational advertising. AdScale is one of the companies that serves up a majority of the display ads in Germany. So the problem here is that a user is loading a website. Which ad are we going to show them? They're loading stuff.co.nz or any similar website, and we have a slot available. We could show them Coca-Cola for a guaranteed 5 cents, or we could show them an ad for a car at 80 cents if they click on the ad. Or we could show them an ad for a mortgage, which pays $20 if they buy the mortgage, but not if they don't. Which one are you going to choose? Which one? You've got 100 milliseconds to make this decision. So the goal is to use the log data generated by these assignments to try and find ads that are more relevant to users. If we can increase that click-through rate, that's the direct path to more revenue for the company. The way an exchange works is that the user is loading the web page. The web page calls up the exchange and says, someone's loaded my web page, I want an ad. The exchange chooses an ad, sends that choice off to the ad server, which pushes an ad back to the user on the website. And the ads are loaded into our system by the ad agencies that actually build these ads. So we're dealing with quite a bit of data here. 10 billion records per month, 3,800 lines a second, a lot higher at peak times at 6 o'clock in the evening when everyone's checking the internet. And we collect about a terabyte of data, give or take, per month. And we often want to analyze 3 or 4 months at once. So you're looking at 3 or 4 terabytes that you need to process, which is quite hard with a laptop with only 8 gigabytes worth of memory. That's our system architecture, which I'll skip for now. So the workflow that I'm trying to do is to transfer the text logs from the impression handlers, the web servers, to Amazon S3, which I'm using for storage. Batch process these logs, do some analysis, push some results from the analysis back to a production database, and then the ad serving code will use these results to hopefully serve more relevant ads. So the infrastructure I'm using is S3 for storage, M1 large instances on AWS EC2 for processing power, and at home I've got my 8 gigabyte laptop and 4 machines wired up for MPI. To start the cluster, you do just what you saw on the demo screen at the start. There's a little tool called Apache whirr. It's Java-based. It's designed to start clusters on cloud resources, so you can use, I think, Rackspace or Amazon. You provide it a little config file, which looks like this, and it will automatically start and automatically configure your cluster for you. Here I've asked it to start 1 name node and 100 data nodes. That's no problem at all. I've done that 3 or 4 weeks ago. There's a couple of, this is incredibly simple, but there are a couple of things you need to know. If you're using cloud instances, you need to tell the Java virtual machine how much memory you want to use. A couple of things like the maximum number of map and reducers, and things like the versions of the software you're going to use. If you can talk to someone who's done this before, that's really, really trivial stuff, but it can result in a lot of pain if you don't know what you're looking for. So I've got a little Python script written that does the job of transferring the data from S3 where it's stored to the distributed file system on my newly launched cluster. You provide the script the IP address of the Hadoop name node, the S3 location of the data you want to move, where you want to put it in the distributed file system, that's like the local path, and a filter if you want to apply a filter to the files that are in that S3 location. Once the data is on the cluster, I now run another Python script on my laptop, which runs a program on the cluster. That's the location of the program file. Again, the Hadoop name node IP, and that's it. Once that script is finished running, which you monitor through the web interface, you transfer the data back to S3, just the reverse of before. And then download it from S3 where it is to your local laptop where you can plot the aggregated, summarized results. Or you can run the entire thing in one line. Start the cluster, transfer the program to the cluster, transfer the results back to S3, pull down to your laptop. That Python script's about 2 pages. It's not very difficult at all. And the only libraries involved here are boto, which is for interaction with the Amazon Web Services, Paramiko, which is just an SSH client, and if you want to get fancy, you can use the Amazon provided library as well. So one of the gotchas here is, let's say we've got 40 M1 large data nodes as part of our cluster, and we're interested in processing 100 gigabytes, which is not too bad. That should finish in half an hour or so. If you transferred the daily logs from the impression handler web serving system into S3 as a daily log file, that tar gzip file might be about 10 gigabytes or something. 100 gigabyte job, that's 10 files. However, Hadoop can't split mappers. Hadoop works by sending thousands of processes all over the data to process it and then aggregate those results back up. Hadoop can't split data that's been gzipped. So if you have 10 gigabyte lumps, you'll get 10 mappers across that data. 10 is not very many, that won't be very fast. You need to split the gzip file up into lots of little bytes. You'll get many more mappers slurping in those small gzip files. Your job will run orders of magnitude faster. And if you have to go back and split up all these massive gzip files, that can be a bit of a problem. The Hadoop distributed file system is based on a 64 or 128 megabyte block size, so it doesn't make sense to go much smaller than that. Other ways of automating clusters other than Apache whirr are things like Amazon's own Elastic MapReduce, which does the work for you. We found that had a lot of problems. We couldn't interact with databases between other libraries that are part of MapReduce. We couldn't make Pig talk to HBase. Massive problem. It's not a finely tuned product. I wouldn't recommend using it. But if you're looking for a simple automated solution, it can work. Cloudera is an amazing open source company. They sell upgraded services. They also produce a graphical cluster manager, which is really awesome if you want to use 3 or 4 machines on an ad hoc basis. And it will skip Apache HBase, which is a column store database. Pig, which you may have seen before, is a data flow scripting language. It lets you write MapReduce programs in Java in an incredibly concise and easy way. 10 lines of Pig converts to 200 lines of Java code or more, and the development time is incredible. This is the log data that we might have simplified. We've got a timestamp, a user ID, an ad ID, a website ID, and a whole bunch of other stuff. If we want to turn that, we can do joins, sums, aggregates, anything you can do in SQL, you can do operations on aggregates and groups and things. For instance, if we wanted to go from timestamp user add website to the user ID, the first time they were seen, the last time they were seen, which URL they've been to and how many views they've been to across a month, that transformation there is basically those 3 statements. So now the Python part. You can look at Hadoop as just a distributed I/O system. Start 100 machines, load 3 terabytes of data. Now it's all sitting there waiting to be operated on by Python. You can do that in 2 ways. You can either write MapReduce programs directly in Python, which is a little bit more tricky, or if you don't need to do maps and reducers in Python, you can just use Python as part of your Pig workflow. You can register the Python program using Jython, because this is all Java, load some data. For each line in the data, do something to it with Python. For instance, this is calculating the vector norm of a list of numbers in a comma separated file. Initial sum is 0, square all the values, add them up, take the square root, return the value for that line. This here, so the live demo that I started before, this is going to count the number of words and count the most popular characters in Pride and Prejudice. That is the entire Pig program. The input is just the book as a text file. This is my Python UDF. For each line, if the characters, if the word in the, sorry, for each word in the line, if the character matches the list of characters here, output it, otherwise output nothing. Those 2 programs are all that's in the live demo. So now that we've loaded and transformed, counted, summed, done some aggregate on some data, Let's do some actual math on it. This is the transform data set. You've got, for one campaign, did the user click or look at it? And at what time, which user was it? What website was it on? And which campaign are we looking at? That's like a simple form of the data set. So let's do some feature engineering. This is more art than science. For what could we use to describe the users? We could look at what times of day they're online. People that online at 10 a.m. in the morning through to 3 p.m. are unlikely to be workers. How often do they refresh pages? Are we going to look at the day across hour blocks, or are we going to look at minute blocks? How do we discretize it? Do we look at how many times they've been to a website, or just which website they've been to? There's any number of ways you could do this, and it's quite important, but it is an art form. For instance, this user here is more likely to be interested in wine and beer, and so the campaign results should reflect that, if this is a bulk wine sale. So some common mathematical approaches you might try at this point would be L1 regularized logistic regression. It's basically linear regression with some tricks to account for lots of dimensions. You could use singular value decomposition or non-negative matrix factorization, or you could look at clustering the data that we've seen before here. So regularized logistic regression, I won't go into that too much, might not have time. Non-negative matrix factorization is basically, let's say, for the users and the ads, this user did really well on this ad here, but not on that ad here. Let's find a user factor, a vector describing the users that's 10 things long, a vector describing the ad. When you take the dot product of those two vectors, you get how the user is likely to interact with the ad. So basically, this was the core of the system that won the Netflix prize, if you've heard of that. I did try this. This is some average click-through rates for different campaigns across websites. These are the pink ones here, the blue ones here. Non-negative matrix factorization. We did get some averages in the right place, but overall it wasn't very successful because missing data. So for one user, they've just arrived, you've seen them for 5 minutes, they've been to one website. Another user who's exactly the same type of person, we've seen them for 3 months and we've got hundreds of data points on them. The mathematical distance between those two vectors is quite high, yet they're exactly the same person, and that tends to screw up the matrix factorization-based approaches. The other issue is the curse of dimensionality. If you have a unit sphere, like a circle drawn around the origin in 2 dimensions, if you've got 100 dimensions, every point is closer to the boundary of that universe than it is to any other point. It's the volume of data, the volume of the space the data is in expands enormously as you increase the number of dimensions. Math in 10 to 20 dimensions and math in 1,000,000 dimensions is totally different. And that causes problems with clustering as well. So this is my thought process as I went through this. How might I deal with this? Let's use the similarity between 2 user vectors and just draw a dendrogram. Let's just merge the nearest 2, treat them as 1. Merge the next nearest 2, treat them as 1. You'll wind up with a structure here. Then maybe if we cut this graph along here, we'll have grouped the people into larger groups that we can work with. And it turns out that this works okay. This is random data. This is what you get after you order it by this dendrogram. So there's definitely some structure appearing there. Another way to start this, so this led me on to how do we sidestep the curse of dimensionality. Let's form a graph by taking every user, finding the 10 nearest points to them, drawing a line between those points and seeing what we wind up with. If you do that, it turns out you get this. And I've clustered this graph using various heuristic methods, and then you can work with the clusters and assign one group, one type of ad to each different type of cluster with the different behavior of the people. This is the degree distribution of that graph. It's roughly power law, although I wouldn't like to claim it is exactly power law, which is a feature you'd expect from like a social network or other real-world network data. Now this works, but it's really hard computationally because to form that graph, you need to say how close is this user to all the other users, then the next user, how close is he to all the other users, and find the top 10. That's n squared. That's quite difficult when you get high numbers. 1,000,000 users takes 6 hours on the 4 machines I've got wired up for MPI, and that's running highly optimized C. 18 million users is not really feasible in those 4 machines, and spinning up more hardware isn't really an intelligent way of attacking that problem. Locality-sensitive hashing or data structures, again, they don't work too well. Like a computer scientist might say, we'll use a tree data structure. In 1,000,000 dimensions, it basically doesn't work. So in an attempt to reduce that computational cost, I moved on to the same graph idea, but let's look at, instead of just looking at the users alone, let's look at the users and the ads they interact with and draw a line of the websites the users interact with, and then we'll draw a line if the user's been looking at the website. So essentially we want to go from a graph that looks like this, where these are users and these are websites. We want to turn that graph into something that looks like this, and then hopefully we've got groups of users that interact with similar websites, people with similar interests, websites that cater to that interest. And this is what I'm working on now. If you do this, you'll turn the matrix, random data matrix that we saw before, into something that looks more like this, where these users are more interested in these ads and so forth. So in Python, a lot of the stuff I'm doing with graphs, you've got a node and a node it's connected to. So you've got long lists of simple data, just columns of numbers, basically. So I've been using Python for manipulating these columns of numbers, for doing things like taking out the little parts of the graph that are only connected to each other and aren't connected back into the main blob. I only want to work with the main blob. Those other little groups are going to screw up my algorithms. So I need to scan through that entire array and remove numbers if they're not connected to any other numbers. So that's a good thing to do in Python, and it's low complexity, so I don't need the speed of C. I might want to turn, a lot of the libraries I'm using are C code, so I might want to get rid of the commas and turn them into spaces or something, just do simple text formatting operations on these lines. Again, I can scan through the line in Python, do those file conversions. But that's hard if your array is 6 gigabytes worth of doubles and you've only got 8 gigabytes of memory. NumPy's load text function doesn't even get started, because if you're loading a 65 megabyte text file, NumPy.load text takes 2 minutes and consumes over a gigabyte of memory. You need to pre-allocate a NumPy array and then scan through that file line by line and fill in the NumPy array. That takes the same amount of time, but an order of magnitude different memory usage. Now, there may be better ways of doing that, but pandas won't do it, NumPy won't do it. My own function is only about 6 or 7 lines. That's basically what I described. So, for instance, you might want to go from this line here. You've got 9 with a distance of 0.14. You might want to drop the distances and just have the node IDs 9, 2, 1, 3, 12, and so on. This is quite an interesting trick. This is a Python function here that takes a matrix and just sums up every entry in that matrix. This one plus this one plus this one plus this one. 2 loops. Not fast in Python. It's an interpreted language. This little decorator here will apply a just-in-time compiler to that function, and the just-in-time compiler is NumPy aware. It was designed to work with NumPy. In fact, it was even written by the creator of NumPy, I believe. For the pairwise comparisons I was talking about before, this is the difference in speed. That's a log scale, so from here to here is 10 times faster. This is the standard Python. This is a Fortran inside Python. This is optimized Python, and this is what the results of the decorator. So it's blazingly fast. It even works when you're writing things out to disk. If I've got a Python function that scans through a long list of numbers and writes that long list of numbers to disk and skips out every line that's the same as the previous line, standard Python, 4 minutes or so. You can drop that with an order of magnitude just by adding this decorator to the top of that function. No other changes at all. Only issues you have to be aware of with doing that are that you should use NumPy data types where possible. You don't use a list, use a NumPy ND array. Use this type of indexing rather than this type of indexing. And you can specify the argument types directly yourself if you want to. And in some cases, you need to do that rather than letting it infer them automatically. And the really annoying thing is that you can't return tuples from a function. That breaks the compiler. Blaze is another library to have a look at for the future. It's basically NumPy, but will run across a cluster in similar fashion to an MPIC program without any programming input. The creator of NumPy has moved on to Blaze. He's been sponsored for this project. And you could eventually write half a dozen lines worth of Python that automatically distributes a program across a cluster, analyzes data, aggregates the results. It's not ready yet, but it's an interesting thing to watch for the future. We've heard a lot about pandas. That's another amazing library for data analysis. And once you've done all this and you've worked out something that works, you've got some cluster work here, you've got some C code here, you've got some Python code here. If you want to put that back into production, the best way of doing it is to try and take the algorithm and convert it into the Java MapReduce system. MapReduce doesn't work for some algorithms, but often with a little tricks or thinking about it, you can do it in this framework. If you can, that's the best way. Otherwise, again, rewrite it all in C. Or maybe incorporate it into one of the expensive vendor massively parallel databases like Vertica or Titan or Neo4j or others like that. So the Python libraries that I've used are boto and boto core, Paramiko for starting and stopping clusters, NumPy, Number, Pandas, and Blaze for the data analysis, as well as my C libraries. And now let's have a look at the results of the live demo. So, we have a cluster. This is the IP of the name node. I'm going to set that in an environment variable. And then I'm going to, I should have done this earlier. Going to run the script. That'll take about 3 minutes, and then we can look at the output. So while that's running, does anyone have any questions about any of the?
So what's the axis on the million dimension thing?
What's that, sorry?
Why is it a million dimensions?
Because the way I was talking about feature engineering, the amount of numbers you can describe to use the user, you can look at all of the search terms that they've used. If the referring URL gives you the search terms they used to arrive at the website, straight away that's most of the English language. You can look at the time stream of the times they've been online. You could turn that into hundreds of thousands, or certainly thousands of points of data, and then compare. So one uses time pattern versus another uses time pattern. Then you've got all the websites they've been to, which at the very most basic is about 6,000 to 10,000. So already you're looking 10, 12,000, and it's not very hard to get up to 1 million, especially when you start adding in natural language.
Does the cloud cost a lot of money, and what sort of order of magnitude to run one of these processes?
The M1.extra large instances have got 16 gigabytes of RAM, they run 4 threads, and they cost about 12 to 20 cents an hour. So if you start that cluster, you're looking at coffee prices to do 2 hours worth of analysis, and you can often do incredibly huge jobs in small amounts of time just by adding more machines and staying within that hour charging limit. If you want to run 100 machines for 24 hours, you're starting to get up to hundreds of dollars. So yeah, it's definitely achievable for paying out of your own pocket to do some of these things.
So you can make a mistake and run it again and fix it?
Yeah, no problem. What you don't want to do is accidentally forget that the cluster's running and come back in 3 weeks' time and find out that 100 machines are still there. That has happened.
$3,000 on the mainframe because I had a spelling mistake in eigenvector and it had a U instead of a V, but you couldn't see it on the dot matrix card. I got charged $3,000 to run the processing and there was no output.
It's a lot better than that now.
Where do you get your data? Do you purchase it from data brokers or?
I'm working with the company that actually runs the exchange. Yeah, so you wouldn't be able to, this is not publicly available data, and it wouldn't be. So it's the same stuff as Google's AdSense network. We serve about 80% of the ads that Google serves within the German region. How's this doing? Still running, 16%. There's a lot of overhead in this framework in starting up and stopping jobs, but what I just did, the config file had 3 machines there. I could have set that to 100 or 1,000, it still would have worked. If that book was 3 terabytes in size, I wouldn't need to change the program at all. It would just work. It's really cool.
How do you select subsets of data to work with on like your local system?
Well, for instance,
Grabbing like a random subset, or do you try and?
well, no. For instance, what's the user lifetime? For instance, we've got 18 to 50 million users, people in Germany in the system at any one time, but a lot of people clear their cookies, so we can't track them beyond where they clear their cookies. So you might want to say, of the 18 million users, what's the duration curve? So that you've got 50 million users and just a number for each duration. That was really important to know, and actually the company didn't know that until I turned up and started doing some of this batch data processing. That's just 18 million times 2 times 8 bytes, a few megabytes. So that would be an example of a tiny subset of data that's really useful for the company to know how long are we keeping track of people before they disappear off the system.
Do you know of a nice way to manage AWS instances, bring them up, take them down? You know, I've never used Amazon Web Services partially because I know if I did, I'd want to automate it, and then I'm worried about automation. So,
If you're looking for things like web servers or auto-scaling or anything like that, you need to look at Amazon CloudFormation. That's their own tools for managing these things. If you're interested in data processing like I am, you've got 2 options. You've got either the Hadoop framework or you've got MPI clusters, which MIT has released a library for called Star Cluster, which manages the sort of the more scientific computation stuff. So you've got what I just described, Apache whirr, Cloud Era Manager for Hadoop, Star Cluster for the MPI stuff, and if you're looking at single instances, then you really are better off writing your own 20-line Python script to do it. And if you want some code to do that, just come and see me and I'll pass on what I've done.
Success.
Oh, brilliant. So I will SSH into the, In fact, where's my mouse? There it is. This is really annoying. No, at least it's etched into the machine. And I store the output for this job on the local Hadoop distributed file system. So we will cat the results. Hadoop file system, cat. Caroline, 17 mentions. Mary, 39. Kitty, 71. Elizabeth, the most popular, as you might expect from Pride and Prejudice. Darcy just behind. And Catherine de Bourgh gets a middling amount of love. So there you go. That could have been the entire Wikipedia core, and all I would have had to change is the number of machines I started.
Couple more questions.
No more?